All right. So as for today, all right, going to continue looking at applications of differential equations. And so we saw the first one, again, the mixing problem, super interesting. This one has a slightly more complicated situation, all right, as we're going to see here. But the main concept of all these still is the same, all right? With these mixing problems, all right, and population that we're going to look at, the change, right, the rate of change of the substance, it's all going to be about, right, the liquid in times the concentration in. Minus the liquid out, or rate out, whatever you want to say, times the concentration out. Because that's the whole concept of basically what we're looking at. Okay, let's look at this particular case. A 1,000-gallon tank holding tank catches the runoff from a chemical process. Initially has 800 gallons of water with 2 ounces of pollution dissolved in it. Polluted water flows into the tank at a rate of 3 gallons per hour and contains 5 ounces per gallon of pollution in it. A well-mixed solution leaves the tank at 3 gallons per hour as well. When the amount of pollution in the holding tank reaches 500 ounces, all right, the inflow of polluted water is cut off, purified, all right, and purified water will enter a tank at a decreased rate of 2 gallons, while the outflow is increased to 4 gallons per hour. Determine the amount of pollution in the tank at any time t. So the important part here, okay, the process is not consistent throughout the lifetime. So, all right, at minimum, all right, we're going to need 2, all right, different equations for the change in the rate of the solution. That's the big thing. All right, so let's start with our first one. And so again, all of this is just, I like to just get it all set up because we have rates in and rates out. All right, so with our information here, all right, so for initially what's happening, all right, how much is going in? What's the rate going in?
3 gallons per hour.
Yep. All right, now be aware that, right, 3 gallons per hour, ounces per gallon, so I know that I have ounces per hour. But it's always good, again, want to watch out for that one trick where this says gallons per hour and this says ounces per, or ounces per, yeah, whatever, another quart, you know, whatever unit, another unit might be. So you have to make sure you adjust. Okay, gallons per hour, all right, and then what's the rate of the pollution going in?
5 ounces.
5 ounces per gallon. So yes, so we see our units can match up there. All right, what rate initially, it's all initially, is it leaving?
3 gallons per hour.
Yep. Right, so how much was in that tank?
It started with 800 gallons.
Yeah, so is that ever going to overflow?
I mean, it's possible. 3 to 5. No.
Yeah, this is liquid in, liquid out. So it's holding steady. That's the whole idea there. All right. Yes. Or it's like in the, I just mean in the first equation. We haven't looked at what's happening in the second really yet.
Okay.
Okay. All right. So remember, right, what we looked at last time. So much salt. So the main concept of concentration, right? Usually it always comes back to this guy, all right? Amount of substance anytime t divided by volume, all right? Now, last time we had to do our volume adjusted because that one, right, like more was going in than was leaving. So we were looking, that was increasing overall. So the denominator being volume, right, does adjust to solution in and solution out. So in this case,
we have some amount. Call this Q1T. All right, all still over our volume. In this case, what's our volume?
800.
800. And is it increasing or decreasing in the first stage? No. Oh, look. So we actually get a nice, clean piece of the equation here. All right. Couple other little notes. So, initially, at time 0, how much pollution is in our tank?
2.
2 ounces, yep. All right. And again, it's always good to keep track of your unit as you're going, right? You got gallons per hour, ounces per gallon. Oh, so that has to be ounces, right? Everything needs to line up. Okay. Now, what we didn't really do heavily on the other one, since there was just one system in play, was make note of the time. This first system, all right, when does this begin?
Time 0.
Time 0. Okay, and then it goes, all right, until when?
This,
Just conceptually. Go ahead.
so the pollutants reach a certain amount, which is 500.
Yeah, till the pollutant reaches, right, this like max level. Okay, so I want to call that TM, all right, just because my notation. All right, and so I'm calling TM equals max pollutant. Because at a certain time, which we're going to have to figure out, all right, this situation changes.
Is it 33 and 1/3 hours?
It's like it's 30. In order to it's 35. It's changed, but in order to find it, we have to do stuff first. Okay. All right. So there's our first equation. All right. Now let's set up our second equation. Okay, so once again, rate in, rate out. Okay, so at this time of maximum pollution, right, our situation changes. Okay, so let's figure out what's happening. All right, so what becomes the rate in at that point?
Purified water.
1 gallon per hour.
Yeah, what's the rate in the liquid? This, when I say liquid in, I really mean rate of the liquid in.
1 gallon per hour.
Or is it 2?
Yeah. All right. So purified water will enter the tank, right, at a decreased rate of 2 gallons per hour, and it's decreased from 3. You're saying it's a difference of 1. Yeah. So it is now coming in at 2 gallons, all right, per hour. Now here's the other thing. What's the concentration of that liquid coming in?
0.
It's 0, right? Because it's purified water. That's the whole idea. Oh, so already, I was like, that's really good news in our equation. Okay, what is the rate leaving? 4. All right, once again, concentration out. Now here's the tricky part of this one. Okay, so definitely Q2 of T. The numerator is a piece of cake. Okay, so in order to calculate our volume, it's basically what we did before. So what's our initial volume when the second process began?
800.
It's 800.
Minus 4T.
Okay, almost. I was like, remember that it's the change. So remember what we did last time, right? Yes. So if we have 2 going in, 4 going out, what's the change? Just 2? Let me clarify. Is the 800 going to be increasing or decreasing?
800 will be increasing.
Increasing?
Increasing.
Okay, decreasing.
It's 4 going out.
right? 'Cause
Oh, okay.
4 going out, 2 going in. So the 800 is decreasing, which means actually, is that just 2? Yeah, hold on. Let me clarify. Is it +2? It's -2. So I just want to clarify that part. Okay, now here's the other weird part. So that part, and I would normally do T as well. But remember last time we used it because our time was consistent.
Different time interval.
It is a different time interval. Very well done. Okay, the time interval on this next one, okay, since I had TM, I'm going to say TE and I'm going to call that time eventually. Right? Basically when the process will stop, because when's the process going to stop here?
But the tank is empty.
Yeah, tank is going to be empty because four out, right? 2 in, 4 out. So this one ends in the other direction. Now here's the other thing. I would absolutely do 800 minus 2T as before because that's what we did last time. We did 600 plus 3T, right? Because overall it was an increase of 3 per time. But because this second process is delayed, I have to offset it by my time of maximum pollutant, right? That's the whole idea, right? When we create these algebraic equations, because I just want to make sure after 1 hour of the new process starting, right? I want to make sure, okay, whatever that is, that difference. So T minus TM maximum pollutant. So this is 1 hour after the new process. So this becomes 1. So 1 times -2, 798. So what we want? Yeah.
Hour outflow.
1 hour after we start this second process. And so you have to make sure it offsets because we want T minus TM, right, to equal, all right, a 1 hour offset. That's the whole idea of this. So every time you check it, all right, it plugs in. Okay, and then one other thing, this process, okay, will be going from TM to D to TE, and this process has an initial starting. So there's two tricks on this one. It does not start at 0, but when does this process start?
0 plus T.
Oh, given our notation.
TM.
TM, right? The first process goes from 0 to TM, which means the second process starts at whatever this, and already notice, right? As we're setting this up, what do we have like a million variables? What's the first thing we need to do?
Define the variables.
Yeah, we need to start finding some stuff because we got too much we've got too many unknowns. So our first step is going to be starting to find a few things. All right, one last little process. So Q2 of TM, right, has how much, right? Equals what? It's not volume.
I looked for the mass of stuff, like 500 ounces of pollutants.
Yes, remember what Q is. Q is pollution amount, which means it actually starts at 500 ounces, right? Our first process, right, started at 2 ounces, right? Q of 0 equals 2. That's a super nice one. The second one is some unknown time that starts at 500 ounces. But this is the other thing, right? We're always matching up all our units, all right, to make sure everything lines up. And then one last little note, all right, just as we proceed. Time eventually equals time maximum, whatever that is, right? Because time was going in, time was going out, right? How long after time of maximum pollutant do we have time eventually? Remember that we are draining at 2 gallons per hour. So
Hours.
what?
40 or
One more.
I said 400 hours.
Oh, you already said 400. Oh, okay, I think you said 4. You said 4, and I heard 4, and then 40, and I was like, oh, we're almost done. Yes, 400. Yes, exactly. So we know that we will have that at the end of our process. Okay, so we got that all set up. Now let's rewrite our and reduce down. So setting up is everything. Let's reduce down our IVPs and see what we have and what we can do. Okay, so we got them all set up. We were able to simplify, and then now we can actually solve. So since I have the most knowns, actually in the first equation, let's start there, right? Second equation, I got TM, I got T and TE. So that I was like, in order to even see where that one starts, I really need TM, which means I should solve the first one, see if we find TM, and identify from there. So with the first IVP, all right, what is that? What kind of IVP is it?
Linear?
Yep. No, keep going. Just linear, isn't it?
Linear first order ODE.
Okay.
Linear, first order, simple, ODE, whatever, like all those descriptive words. But the whole idea is that, yeah, oh, that's our standard method. Okay. I can get that into the correct form. All right. And we are at the stage where we should be able to solve this. Setting up is the good part of these problems, right? That's a first order simple linear ODE, right? Which we could solve with integrating factors. It would be all just details. And so let's make a note that Q1 0 equals 2. That isn't going to solve that and find C. With that, all right, now I actually have an equation, and now we can finally do something real, because this equation goes from 0 to T maximum, which means, all right, if I have T maximum, I'm trying to find T maximum. Remember this equation, all right, what does Q represent again?
The mass flow rate.
Okay, mass flow. Specifically in this context.
The flow of pollutants.
Yeah, not flow, amount. Yeah, it was the rate of change of the flow of pollutants is the derivative, right? So Q is actually the amount of pollutants. Okay, T maximum pollutant time, right? That's what we're trying to find. TM. How much pollutant will be in our system? 500, which means that if I have, so Q1 of T equals 500, I should be able to solve for TM, which means I could just set those two equations equal. Solve via graph. So many hours. So once I have that, now we can start identifying other pieces of information. So to our Q2 we go. And I can plug that in so I actually know. And remember, this one is just 400 hours later. Simplifying it down and multiplying some pieces out after I plug in TM, right? Then I should have this system of differential equations, right? I now know, at least we know the maximum time eventually at the end of our system, all right? And then in order to solve this guy, how do we solve this one? And the Q's sometimes kind of throw it off.
Wow. Split it up. Forget about
Yes, it is separable. You're absolutely correct. All right. So sometimes this is why I remember we jump back and forth between prime notation and like dq dt. Because if you write this as dq dt, that's q. Oh look, I was like, that guy goes over. I was like, and we can actually pull those pieces out. All right. Also, the point is we went over many examples of separable equations. So when we get, as our problems get more complicated, I leave more and more of those details to you. Because that solves, it's easily separable. We find our solution, and then here's the cool part. Because this is, all right, a process, okay, that has one set of equations for one part of it, and then a different equation for another part of it. When we put those together, what kind of, if two different equations is represented as one function, what do we call that? Usually, like there's a parenthesis and then some
piecewise function.
piecewise function, right? Just refreshing us on our notation, on our verbiage. So this whole process is actually a piecewise, where I can represent Q instead of Q1 and Q2. And what is really interesting, so when we graph this, it basically has a sharp uptick as represented, right? It is an exponential. And then flows down, drops out. So around 35. So it actually is very, very nice, all right, representation of a system, right? Oh, pollution's increasing, and then all right, drops out until the tank is empty. So I was like, the change in the process, very, very, very interesting. Identifying our types of equations, and notice we don't have that many. Without a doubt, first, foremost, the most popular simple first order linear differential equation. Separable, I said, is our second most popular. Oh, look, this had both of those. The potential function equivalent, whatever. Exact equations, much less common and usually easy to identify. All right, and Bernoulli, those are kind of easy to identify too. Without a doubt, separable and first order simple linear differential equations, those are the most two common, and those are the ones we solve the most. Okay. All right, so mixing equations. All right, very, very interesting stuff. A similar, all right, problem to mixing equations is population problems. Same kind of stuff, all right? PT represents the population, and hence the derivative of that represents the change in the population. The concept is also the same as far as our calculation of value minus value. Rate, population enters the region, minus rate, population exits the region. The exact same concept as flow in, flow out. Let's see. What's different this time is what is entering and exiting. So what is increasing, right? Population rates, right? So we look for anything about birth rates, migration into the region, all right? When exiting the region, we're looking for things to the nature of death rate, migration out, predation rate. So basic same things, except now we have multiple things instead of just liquid in, liquid out. All right, so different types of things entering the region. Let's look at an example. Population of insects in a region will grow at a rate that is directly proportional to their current population. Okay, directly proportional. We'll come back to that in just a minute. In the absence of any outside factors, that's big wording as well. Okay, lots of things to pay attention to. Population will triple in 2 weeks' time. On any given day, there is a net migration into the area of 15 insects. 16 are eaten by bird population, 7 die natural causes. There are initially 100 insects in the area. Will the population survive? If not, when do they die out? Okay, so let's start with the very first part. Population of insects in the region will grow at a rate directly proportional to their current population. Okay, so if we have, right, P is our population. And we could identify that as P of T as well. But directly proportional. So do you guys remember proportionality? How do we deal with that?
Is like a
What operation is that really?
multiplication.
Yeah, it's just multiplication. So the whole idea there is that, so we're basically identifying that birth rate is some number times P. All right, since it's directly proportional to its population, all right, R, W, whatever you want to call it, K. So, okay, so we got our proportionality. Overall, we can create, let's create the whole AVP in them. So, the change in population. All right, so growth, yourself weird. Please. Okay, so what is entering or increasing our population? So without a doubt, birth rate. So something about RP. What else do we have?
That condition that every 2 weeks it triples.
Oh, gonna come to that.
Okay.
Just the flat numbers. What else is increasing?
Net migration into
Yep.
a 15.
All right. And then exit, yeah, 16 getting eaten
And then 7 die.
and 7 die. All right. Once again, population at time 0 is then what? 100. Okay, so that's at least the initial setup of the info. And if you reduce that guy down, P prime, this actually then becomes bar P minus 8. So now you're absolutely correct. Okay, so I have that guy in the absence of any outside factors. So what does that mean? What does that mean we're going to ignore?
The birds.
Predators.
So that means, right, no outside factors. That means no migration in, no migration out, no predation. It ignores everything. It means we only care about what part?
Growth.
Birth rate. You're absolutely correct, right? Just the birth rate. So birth rate will triple in 2 weeks' time. That means no outside factors. My equation becomes P prime, R P. Once again, P0 is still 100. But we are told what other part?
After so T plus 2 or time plus 2 weeks. I remember where our time interval is.
Ah, okay. It's super important cost. So we keep saying T equals 0, right? What is our time interval here? So 2 weeks. So is that all we're looking at?
Days.
Days or weeks? Which is it?
On a given day. So any day, so we gotta convert everything to days.
Ah, well done. Right? This is finally the case that you were saying, oh, yes. Sometimes you have to watch for this because the migration, right? Now, could I convert it the other way? So 7, so what
23 times.
yeah, so yes, so exactly. Increasing all these numbers in order to turn it into weeks or 1 week or 2 weeks, however we want to do it. But it's just way easier since all this is days. It's way easier to convert 2 weeks.
14
days. But however you want to do it. All right. And so, all right, whether you do that immediately or when you finally need it, all right, that's the important part. Okay, so population will triple in 2 weeks' time. So P of 14 equals what number?
300.
Yeah, 300. Right? We don't need to do 3x. We can actually just calculate it as is. Once you have that set up, all right. Again, this is a separable equation because what I need to actually find here, all right, is R. And here's the coolest part about this one. The equation, all right, this is a separable differential equation, results in this. Does this look familiar?
for like physics a little bit, like, but
It should be for everything.
it's a growth. It's like
It's the growth rate.
Yeah.
This is the relative growth rate equation. It's used in everything also.
banking and
Yes, yeah, I was gonna say compound continuous.
Yeah.
Like, yes. Oh, look. So look. Oh, see, isn't it beautiful how the differential equation? I was like, we basically proved something that we use all the time. I just love it when this is one of those things where it's like I get this and I'm like, well, I guess I'm on the right track because I have a relative growth rate equation. I don't know, that's just fun.
Is that gonna be true of all population
Well, okay, what?
questions, if you
What
will?
was the key wording in this?
That's growing and you have some death and,
Yeah.
Okay.
Proportional, it's growing proportionally,
okay,
right? And then, I mean, no outside factors, the equation always gets more complicated.
you have those like
If you have outside factors involved.
those coefficients that modify stuff, right?
Yeah. Okay, so with that, then we can identify, right, we have P of 0 is 100, which means 100 equals C e to the 0, which gives us our C value. Similarly, then I need to apply the other condition. Plugging in those pieces then gives me R equals ln of 3 of 14, which is what we were finally trying to identify, because what we really needed was R. C was kind of a means to an end in this situation. So our original differential equation becomes, right, P prime equals, and remember we had RP minus 8 here. So P prime equals constant P minus 8, still with our initial condition. All of that was really just to get what proportional rate is the birth rate increasing by. From here, what kind of equation is this?
Linear, first order.
Simple is the other word. Yeah, I was like, first order linear is typically what we call it, right? I was like, I think the full definition is simple linear first order differential equation. But yes, that's the important part. So yes, this is clearly linear first order simple DE, which means we can solve that guy down. And this brings up something kind of important. I bounce back and forth between exact and decimal, and I don't, whatever is easiest in the moment, try and be exact when you can, but I give up plenty. And as we see, especially when we get into our next couple of chapters, as the numbers get worse, I go to decimals more often. Now I try and be precise, all right, as much as we can, because especially when we start doing like the spring systems. But just do your best. I was like, I don't really care one way or the other. You have the answers in the home one. Verify, like if I wrote it exact and you wrote it in decimals, make sure they're the same, or vice versa. But a lot of it is just whatever I feel like at that moment, and how annoyed I was at writing how complicated it was. Like,
Yeah.
all right, so
Real quick, if that's the case, do you have a preference for how many decimal places we carry out these things, or how many sig figs, or use your best discretion, or?
best discretion. I am a fan of 4 decimal distances, just because it's stats, like,
Is
that's what we do.
the standard, right?
Yeah, it's the standard, so I
Okay.
was like, but even here, when I
It's
was
6.
5, just
Oh, fine.
randomly, like, I mean, so, no. Do not care, looking for the concept versus the precision. I was like, Liz can keep you guys honest for precision. I was like, I want to make sure you understand process.
Okay.
And the details get long already. I was like, so we saw those examples we did of linear first order differentials, separables, all the grinding we already did. I was like, that I'm skipping here. The details are solidly 20 minutes in this problem, right? So just be aware of that. Okay. Then the last important part. So just by definition, right? Just looking at this differential equation, is the population going to be increasing or decreasing? And right, just because this number is small,
It seems like it should be decreasing.
it's decreasing, right? So I can go and I can plot this guy as well. And we at least know our starting point,
100.
100. And you plot it, and it would look something, right? It's semicircle-esque. And then once again, all about the calculator whenever we can. Right here, this guy, 50-ish, you would find T equals 50.44. And then what were the units?
Days.
Days.
Them buggies are no more.
So setting up the equation, I always find setting up the equation and identifying the details way more exciting, right, than the last little bit. Like I love setting it up and then, oh, no outside factors. Oh, relative growth rate. Like that's the cool stuff. And that's why I definitely skip this step here, because once I identify it's linear first order, then I'm like, okay, integrating factor, and I just gotta grab through the details. All right.
There's going to be tornadoes in the Midwest today.
Oh yeah.
Yeah. I think a 5 to 10% chance in parts of Indiana and Illinois.
All right, one last problem. So 3 types of problems that you're going to see in the home fund: mixing problems, population problems, and falling body problems. Without a doubt, falling body are my least favorite, mostly because, just like you guys, they've been beat to death in there. I was like, I've just seen it so many times that it's just like, yes, okay. Like, but it's once again something we need to mention, mostly just because this is just the perfect definition of a differential equation, right? It's what we started the class with. This is not the last time we're going to look at it, right? In the second law of motion, all right, F equals ma, or turning it into v, or even double second derivative of position. The only thing is that, and now of course it'll work both ways, but convention, whenever doing falling bodies, I always use down as positive. Do you have to? Absolutely not. I just like to be consistent there, and I like to, down being positive just feels way easier to me. Oh, one other note. So on our upcoming quiz, not a secret, my favorite problems are mixing problems. Going to probably be one of those. This is on the home fund and stuff, but I was like, I tend not to test on it. Like, okay. A 50 kilogram mass is shot from a cannon straight up with an initial velocity of 10 meters per second off the bridge. That is 100 meters off the ground. If air resistance is 5 proportional to velocity, determine the velocity of the mass when it hits the ground. Already, okay, so we have a kind of assumption we're making. If I am standing, right, on a bridge, okay, and I shoot something straight up, what's going to happen?
It should fall back in your head.
Yeah, I'll fall back and hit the bridge and it's over. All right, so we are yet again doing the convention that we're shooting it straight up, but we are somehow hovering the cannon over the bridge so it doesn't hit the bridge. So already we're in fiction, and maybe that's why I always hate these problems. I was like, but just a couple of conventions. S equals 0. All right, my positioning is there. All right, we're up here. This is where the bridge is. And then down here, S equals 100 meters. This is the ground. So again, my convention, this direction is the positive. And that's how I set these up a little bit faster that way, that's all. So we have our object, and overall this whole distance, right, is of course 100 feet.
Meters.
Meters, thank you. All right, so a couple of things. We have the object moving up. And similarly, we'll have the object moving down. All right, let's start with the down because that one. In down direction, we have gravity, which we use with what wonderful formula?
Are you talking about the actual gravitational formula?
No. Just second law of motion.
MA?
Yes, but when
It says A, so G?
yeah, and G.
9 point, okay.
I was just gonna say, I was like, when we have the yes, MA is correct. Newton's second law of motion, but acceleration is gravity. And then in the opposite direction of that, always, we have our air resistance. In this case, it was actually told to us, all right, as 5V. And now here's the part with the conventions. Positive is in the down direction, which means air resistance. And air resistance is always in the opposite direction, but this one is going to be negative. Now, down is the easy one, okay? So the object shoots up and then goes down. So that's the one that we exactly expect. When we shoot the object up, once again, gravity is going to be there. But when the object's being shot up, which direction is the air resistance? Does it match this other picture?
No, they're both going to be negative.
Ah.
We're slowing the ball down.
It's going this direction. FA equals 5V. Okay, but here's the thing. All right, air resistance by definition is always contrary to whatever direction the position is moving. So is this positive or negative?
It should be negative if you're by up.
Yeah, it's still negative, which means here's
MG should be negative too because they're pointing in the same direction.
except MG is going still in the positive direction. Air resistance is only negative because it's going in the opposite direction of the object. All right. So MG is still heading towards the positive direction. The whole idea here, all right, since air resistance is always opposite, all right, of whichever direction the object is moving, with our two equations, I can then set up, once again, Newton's second law of motion by definition, where in this case, Fg will then just simply be, all right, the force of gravity minus the force of the air resistance, whether we are going up or down. Both equations actually end up being the same thing. because I have air resistance in the opposite direction that the object is moving. Since I ended up with both equations that are the same, I can just have one, and we can then identify a couple of pieces. So just given we have position information as well, and of course, in order to actually do the IVP, we really only need the initial velocity. So what was the initial velocity? 10. Because down is the positive direction, which direction was the initial velocity?
-10.
Negative 10. All right. Initial position, S of 0.
100.
Zero.
Okay.
Yeah. So again, this is just the conventions that I did. S of 0 equals 0. And then I called it STE. I just like that. Time eventually something happens at some point.
100.
100, right? When it hits the ground, that's what's going to happen. So I can identify my initial pieces of information. With my equation, I know that then M equals 50 kilograms, and we can do G equals 9.8. I'm just going to do 9.8. I know it's 9.81, and there's even more after that, right? So I'm just going to do 9.8. So we can actually plug that in, get our values in. And we actually then have our IVP set up. This should actually look pretty familiar. What? Okay, besides it's just kind of standard. Did we do this a couple of weeks ago? Oh, this was that initial.
One, like,
Yeah, this was our initial directional field that we looked at. This is once again simple, linear, first order. DE. Once we have all the details found out, V of T equals I can then find the velocity, and yet, of course, once you have velocity, what other wonderful thing do you always want to find?
Acceleration.
I mean, yes. And what other? Okay, there's 3. Right?
Position.
Position. Right? Since acceleration is the easy one because the with not that position, sorry. But I could then also find the position equation, which is, of course, the integral of velocity. And especially since we already have initial conditions for that, I can find this complete equation, and that'll also help me find time eventually. So our position equation then becomes with the position equation. All right, what were we actually trying to find? Sorry, not with the position equation. In general, what did we want to know?
The velocity when it hits the ground.
Yes. Okay, so
Before it hits the ground.
we got to identify absolutely when it hits the ground, right? We have our t time eventually, all right? So if time eventually equals 100 meters, that means I can then,
Solve that for 100 or plug in 100, solve for t.
that is absolutely correct. That means S of t equals 100, right? And solve for t. And specifically, time eventually is what we identify. That gives us t equals negative 3.32 and 5.98. Obviously, which one is the correct answer and which one is not allowed?
You can't have negative time.
You can't have negative time. We were then lastly trying to find the velocity. So that means v of 5.98 is what we're actually looking for. Get to just plug that guy in. 38.62 meters per second. And again, whether you use 0 as ground and 100 as the bridge, it all, of course, will work the same, positive, negative. I was like, having done these a million ways, I was like, whatever you prefer, of course, it works out. One last little note. So again, notice, right? We had two situations because that initially started with two differential equations, right? Going up and going down, but they just turned out to be identical. Okay? That definitely does not always happen. Just depends upon the situation. Clearly, we saw in those mixing problems, right? That they get complicated. You need two distinct equations and you have to plug through them one piece at a time. Identifying the information, setting it all up, that's what takes the time. Read carefully. All right, you're going to definitely see that in the home funds as well. Okay, so focus on the setup and just keep going back. The general concept is crazy easy of all this. Rate in, concentration in, liquid in, population in, whatever it is, minus, rate out, liquid out, concentration out. Like, I mean, the concept is simple. It's the details, right, that can get a little messy. And then again, conventions, again, whatever you use, it's up to you. Just make sure you are consistent and remember the consistency. The big thing is like if you're used to always doing it the other direction.
Straight up.
Yeah. Then I see people who try and use my conventions and your conventions just like what you did with the books, right? Like whatever you use doesn't matter. You just have to be consistent. All right. That is absolutely everything for chapter 2.
Woo.